Okay, thanks for the introduction. So this is a joint work with Andrew Childs, Tongyang Li, Jin-Peng and Ruizhe Zhang from all different institutes. So let me start with some motivating questions. So what we can do with fault-tolerant quantum computers, we can, of course, break our crypto systems using by factoring integers, and we can also simulate quantum dynamics. We can speed up the machine learning optimization and scientific computation. For example, we can solve linear systems faster than classical computers. And we can also sample from some probability distributions faster than classical computers. So this is the focus of this talk. So let me first tell you something about the relationship between classical sampling and the quantum sampling. Okay? So suppose we have a probability distribution rho, whose probabilities are P0, P1, up to Pd minus 1. And a natural idea for using a quantum computer to sample from this distribution is to prepare this quantum state, where we just encode the probabilities into the amplitudes. And then if we measure it, okay, then it's equivalent to we just sampled from this probability distribution. So a critical question to ask is then how efficient we can prepare this state. Okay? Another question is, for any classically efficiently sampleable distribution, can we always efficiently prepare the state? So it turns out that this is a hard question, because if the answer is yes, then we can solve a graph isomorphism in quantum polynomial time. So we certainly don't hope we can efficiently sample any classically efficiently sampleable distributions using quantum computers, but at least for some special cases, we hope we can efficiently sample from it using quantum computers, and we can even get quantum speedups. So let me talk about the special distributions. Here we consider today in this talk is called Log-Concave distribution. So what is the Log-Concave distribution? Consider a convex function f. Then the distribution proportional to e to the minus f is called the Log-Concave distribution. And the goal is to sample from this distribution. And there's a closely related problem, which is to estimate the normalizing constant for this distribution, which is defined by this integral. Okay? So why do we care about these problems? Because they have many applications in machine learning, optimization, statistics, and physics. I'm not going to talk about the applications, but I'm going to talk about the methodologies to do the sampling and the estimation. Okay? So before I talk about the main result, let me tell you about the parameters of this problem. So again, this function f is a convex function. It maps a d-dimensional point to a real number. So this d is dimension. Okay? And we also assume this convex function is L smooth and mu strongly convex. That means the second order derivative is upper bounded by L and the lower bounded by mu. Okay? And we use kappa to denote the condition number, which is L by mu. So here, the two most important parameters are d, dimension, and kappa. So the question is, how many queries to f do we need to make in order to sample from this distribution or to estimate the normalizing constant? So we characterize the number of queries in terms of kappa and d. And classically, the state-of-the-art result is due to Ge and Lu in 2019. And we aim to get quantum speedups from their results. So these are part of our main results. So classically, the query complexity for the sampling task, the query complexity is kappa times d. I'm omitting the big O notations. Okay? And quantumly, we can get quadratic speedup for a condition number. And in particular, if we start from a distribution that is good enough, I mean, the overlap between the initial distribution and target distribution is at least some constant, then we call it warm start. If we have a warm start, then classically you can do better in terms of the dimension. And quantumly we can do even better because we have all the speedups for all parameters. And for the problem of estimating normalizing constants, this is classical cost. This is classical query complexity. And quantumly we get the polynomial speedups for all parameters. And in addition, we show that a lower bound for estimating the normalizing constant is at least 1 over epsilon. So that means this bound, the dependence on epsilon is tight, so there's no room to improve this dependence. Okay. So before I talk about the methodology for these two tasks, for the results, let me give you some classical background on Markov chain sampling. So how do we use Markov chains to sample from some probability distribution? So this is the Markov chain. The Markov chain contains a number of states, and there are transition probabilities defined from a state to every other state. So classically, people just start from an initial distribution and they just keep walking randomly according to the transition probabilities. And they hope that after a number of steps, the probability distribution will converge to something you want. And then by this way, you can sample from this some probability distribution. So the question is, how many steps you need to walk for? I mean, what's the mixing time? So it depends on the following 3 parameters. The first is delta, which is the special gap of the transition matrix of this Markov chain. And the second parameter is lambda. It's the overlap between the initial distribution and target distribution. And third is the third parameter is epsilon, which is the total variance distance between the resulting distribution and the target distribution. So it turns out that the classical mixing time is upper bounded by this 1 over spectral gap times this log factor. Okay, so the dependence on overlap and epsilon is in the log factor, so they don't matter that much. So the dominating cause is this 1 over spectral gap. So in order to sample from some distribution, you start with the distribution, and then you build design this Markov chain so that you can so that the stationary distribution is something you want. And for this task, for this sampling from this Log-Concave distribution, the Markov chain we use is based on this Langevin dynamics. Okay, so this is the stochastic differential equation, and this is just the continuous time version, and for the algorithms we need to discretize it in times. And this WT is the Brownian motion. Okay. So now we have the classical background for sampling. Let's give a first try for achieving quantum speedups for the classical sampling. So the quantum counterpart for the random walk is, of course, quantum walk, right? So we start from this quantum walk operator, U of W for Markov chain W. We can always build this operator. And this quantum walk operator has a nice property, which is that suppose pi is the stationary distribution of this Markov chain. Then its corresponding distribution state, cat pi, is the unique eigenvector of the quantum walk operator of eigenvalue 1. So let's see how we can use its property to get this target distribution state from this initial distribution state. Okay. First of all, we note that a reflection about this initial distribution state is easy to implement because we assumed the initial distribution state is easy to prepare. Okay. Then, how about the reflection about the target distribution state? So we use the fact that this target distribution state is the unique eigenvector of eigenvalue 1. So recall that for any unitary operator, the eigenvalues are in the form of e to the I phi for some phase phi, right? So if the eigenvalue is 1, it means this phase is 0. So we can use phase estimation to detect this 0 phase, and then we do reflection about it. Then we can implement the reflection about this target distribution state. Now we have 2 reflections. So does that remind you of anything? So the 2 reflections is the same with 1 rotation, right? It's Grover. So we can use Grover iterator to rotate from this initial distribution state to the target distribution state. So that's it. So what's the cost for this procedure? So the cost depends on 2 things. The first is the cost for implementing the phase estimation. The second is the number of iterations. So let's first look at the cost for implementing this phase estimation. So the cost depends on the number of qubits in the control register for the phase estimation, right? And the number of qubits depends on how easy you can distinguish this zero phase from the other non-zero phases. And it turns out that this phase gap is quadratically better than the spatial gap. So that means we can use 1 over square root delta queries to implement this phase estimation. It seems we have a quadratic speed up on something, right? So, but what about the number of iterations? It depends on the overlap. So, recall that the overlap is lambda. So now this number of iterations is square root of 1 over lambda. Okay, actually this is the MNRS quantum walk search framework. And so is this good enough? Is this cost good enough? So let's recall the classical cost. Classically, the dependence on the overlap is in the log factor, but now it's it's polynomial factor. So in our case, and also in many other Markov chain sampling tasks, the initial distribution is pretty far away from the target distribution. That means that this overlap is pretty small. So now the quantum algorithms is worse than the classical algorithms, right? So this polynomial dependence on this on this overlap is problematic. So how do we get around with it? We get around with it in the special case, in the scenario where we have a sequence of slowly varying Markov chains. So now we have let me talk about the classical here, so that we get back to the classical case. So we have a number of Markov chains, W1, W2, up to WR. And each Markov chain has its own stationary distribution. And we also assume that the special gap for each Markov chain is delta. Okay? Then the reason we call it slowly varying is because the overlap between the adjacent distributions is at least constant. Right? Then classically we can do this. We can start from initial distribution, and we keep walking according to the first Markov chain until I get mixed for the first distribution, and then I just keep walking according to the second Markov chain until I get mixed for the second distribution, and I keep going until I get mixed for the last probability distribution. Okay, so I hope this. So we hope that this is close to what we want. So what's the cost for this? Recall that the mixing time for each Markov chain is the 1 over special gap, and there are R Markov chains. The total cost is R times 1 over delta. Okay, so this is some classical background, but this is not quite useful in classical sampling, because for classical sampling, the dependence on overlap is in the log factor. So using this doesn't save you anything, actually. But this is quite useful in the quantum case. Okay. So now let's get back to the quantum sampling task. Again, we still have we assume we have a sequence of slowly varying Markov chains, and in addition, for each Markov chain we can build the quantum walk operator for it. Now, we start from some initial distribution state that is easy to prepare, and we can build we can implement the reflection about this and the reflection about this. Then we use Grover iterators to rotate from here to here, right? And then I just keep going until I get to the I rotate to the last distribution state, which should be close to something I want. Okay. So the cost for this one is, okay, classical cost is R times 1 over delta, but here is R times 1 over square root delta, because the special gap, because the mixing time, the phase gap is quadratically better than the special gap, so the cost for implementing the phase estimation is 1 over square root special gap. And now there are R Markov chains, so this is total cost. So we can choose this. We can design the sequence of slowly varying Markov chains carefully, so that this cost will be better than the classical cost. Okay. So now let's see how we can use this framework in the sampling task. So we first set a sequence of parameters, sigma 1, sigma 2, up to sigma r, where sigma r is large. And we also define this basic function f0. It's quite simple, and e to the minus f0 is Gaussian, so we can easily sample from it. And then for each I from 1 to r, we define this function f sub I, which is the target function plus something. Because this sigma r is quite large, so that we know fr is approximately f. Okay? And now, for each fi, we just build a Markov chain based on Langevin dynamics for it. And we know that the stationary distribution for each Markov chain is proportional to e to the minus fi. So the stationary distribution for the last Markov chain is approximately something we want. Okay? Then it can be shown that the overlap between the adjacent stationary distributions is at least constant. So this is good. And we can bound the spatial gap, we can bound the 1 over delta for each Markov chain, which is upper bounded by kappa d. And we can also show that the number of Markov chains or the length of the cooling schedule is square root d. So if we put everything together, so the total cost is just r times 1 over square root delta, which gives us square root kappa d. Okay? So classically, you just run the Markov chain, and the classical cost is kappa d, but now we have square root kappa d. So we have quadratic speed up for the condensation number. Okay? Now, this is how we did this sampling. But what about this? The problem for estimating normalizing constant. We still have the same setup. We have the same sequence of cooling schedule, the same sequence of Markov chains. And then, because each Markov chain has this stationary distribution, and we have that each Markov chain has this normalizing constant z sub I. Okay? And because fr is approximately f, so that we know zr is approximately z. This is something we want to estimate, right? And we also can write zr as this telescoping product. So in this telescoping product, z sub 0 is easy to compute. But for the subsequent ratios, okay, suppose we can estimate each ratio, then we just multiply them together, and we just have an estimate of this normalizing constant, okay, right? So the problem is, how do we estimate each ratio? To estimate each ratio, we just sample points according to the distribution rho sub I. And it turns out that this ratio is the expectation of some random variable gi, where gi is defined in this way. So, we just in the algorithm, we just generate IID samples. Classically, we just generate IID samples according to this distribution, and then we compute the function g sub I, and we just do the average. We just compute the average. Then the question is, how many samples do we need? And also, how do we use quantum to do this? Okay, so it turns out that the relative variance for this random variable is constant, and then we can use this non-destructive mean estimation where Jensen just talked about in the previous talk, and we can show that we need this r over epsilon copies of the initial state. Because it's non-destructive, we can use this copy. We can use this copy to estimate this ratio, and I keep using this state, and I rotate to the next stationary distribution state, and then I keep doing this estimation. Then I can estimate them together. Okay, so we just put everything together. This cooling schedule, length of cooling schedule is square root d, and this 1 over delta is upper bounded by kappa d, and the total cost is this. So we have speed up for all parameters. And this is I just summarized I just talked about a subset of our main results. This is the whole table of our result for different settings, different assumptions, and so on. And thank you so much for your attention.
Okay, thank you for your talk. So any questions?
Thank you. Can you maybe comment on the connection to Grover-Rudolph of sampling from Log-Concave distributions? Paper from 2002.
So how do you use Grover-Rudolph to sample from Log-Concave distributions?
Well, they have a paper generating the superposition of Log-Concave distributions.
I'm not familiar with that.
But there was, okay, maybe there was a problem with I'm not sure that this immediately implies, so I don't know, I wondered if you know the connection.
Okay.
Okay.
Hi, thanks very much for the great talk. So, in the field of classical Monte Carlo, I think people would typically do parallel tempering to speed up the mixing time. And can you also do that in your case as well to speed up?
You use parallel
tempering for your case as well. Is it possible to do it?
I'm not sure. So here for this state-of-art result, it just used a variant of this Langevin dynamics to get this kappa D dependence. I'm not sure if you can parallelize it to get a better cost in this result. I'm not sure if you can parallelize it.
Okay, thank you.
Okay.
So these log-concave distributions are well known to be related to convex bodies. In fact, a kind of generalization of convex bodies. And there is some, I think I remember some classical, non-trivial classical result that it's possible to efficiently approximate the volume of a convex body. So I'm wondering whether you get a quantum improvement for that question from these methods.
Yeah, so actually there's a work in QIP2020 talking about this quantum algorithm for estimating the volumes of convex bodies. And also I think in Jens's work, they also improved that the complexity by using the unbiased non-destructive mean.
Well, are the algorithms that you're presenting for sampling, and are they somehow analogous or in the same?
It's similar to this. It's similar to this estimating normalizing constant, which have a telescoping product, and we estimate each ratio and we multiply them together. It's in this way.
Okay.
Yeah.
Okay. Thank you.
Yeah.
Okay. Any?
Thanks for a nice talk. Is there some connection to the quantum Monte Carlo algorithm for speeding up evaluation of integral?
What do you mean exactly by quantum Monte Carlo algorithm?
There's an algorithm to having quadratic speed up in evaluating integral. Maybe I can. Because I'm asking this because basically Grover-Rudolph showed that if you have efficiently integrable function, you can prepare the state whose coefficient is efficiently integrable. Then I thought there's some connection that you might know, but I will come to you later, maybe.
Okay.
Yeah.
Later.
Yeah. Thank you very much.
Okay, so I think we have time for one short question.
Thank you for your talk. A quick question. These quantum algorithms say that quantum annealing method, I guess, requires the chain to be reversible.
Yeah, yes, yeah.
However, I think the unadjusted Langevin dynamics sometimes are not reversible.
Yeah, this is a great question. So, yeah. So the Langevin dynamics we use is MALA, is the metropolis adjusted Langevin dynamics. This is the reversible. But so this is here. So here, this is something I just talked about. And for other Markov chains, unadjusted Markov chains, they are not reversible. So we cannot use this framework to get quantum speed up. So we just use the quantum gradient estimation to get speed up.
Okay, so the annealing quantum annealing method is only for the MALA, right?
Yeah, just for MALA. Yeah.
Thank you.
Okay, thank you. So let's move all the other questions offline and thank the Chunhao for the